All right, so we start off chapter 2, and chapter 2 is all about logic, trying to create a logical thought process, applying some reasoning, and doing that so that we can work on proofs. And proofs are nothing more than arguments. We're trying to make arguments and trying to do so effectively. So that's what we're working on now. For today, we're going to work on the first two sections, which uses what's called inductive reasoning to make a conjecture, to make a conclusion. And then we'll talk about conditional statements. Okay? So, first and foremost, what is inductive reasoning? Some definitions here for you. If you want to stop the video for a second and write these in, we'll pick up what this stuff means in just a second. Okay, so inductive reasoning is all about the process of observing data, right? So observing data. Sorry, I'm trying to get my highlighter out here. Recognizing patterns, that's kind of the big thing there, and then making generalizations about those patterns. So we're using patterns to make a conclusion or a generalization. That generalization is called a conjecture. So we want to make sure that we understand the vocabulary terms here, right? So we're going to use patterns and some data and make a conjecture, make a conclusion. And those conclusions may or may not be true. There may not even be a way for us to know if they're true or not at the time. Okay? So for example, a scientist dips a platinum wire into a solution containing salt, passes the wire over a flame, and observes that it produces an orange-yellow flame. So she does this with many other solutions that contain salt, finding that they all produce an orange-yellow flame. Make a conjecture based on her findings. So if you were to do this, what would you start to think? What would you decide? What would you conclude? What do you think she concluded? Right? It might make enough sense to suggest that any salt solution will produce an orange-yellow flame. Okay, now, do we know that to be true for sure? No, I mean, we haven't tried every salt solution known to man, but that seems to be the pattern, so that's going to be the conclusion that we make. Now, how long will we believe that that's true? Well, all the way up to where we have a counterexample. We would need something that would tell us that it's not true. So a counterexample is a specific case for which the conjecture is false, right? So I'm going to believe that any salt solution is going to produce an orange-yellow flame until I find one that doesn't. And then I'll have to readjust my thought process as far as that orange-yellow flame goes, okay? A little bit more concrete example, an example of a counterexample is if we try to find a counterexample for this belief. I went to the grocery store, all the apples I saw were red, so I decide all apples are red. Now, we know that's not true. And the reason why we know that's not true is because there are green apples and there are yellow apples. So I can produce an example where that thought process is wrong. I can show you a green apple and say, see, all apples are not red. Okay? But just keep in mind that a conjecture is a conclusion that is based on inductive reasoning. Those patterns, it's all we're going off of. So sometimes they're true and sometimes they're not. Okay? Now, another way we're going to use inductive reasoning, and we do this a lot in math, is pattern in numbers, right? So in these two examples, find the next two terms in each sequence and explain the pattern used. See if you can find the pattern first. Explaining the pattern can be kind of tricky. So give it a shot, stop the video, see if you can come up with the pattern, write the next two terms out, and then try to write down what your pattern was, and then we can adjust it. You can adjust it if you need to. Okay, so I believe in your notes, we even try to help you out by suggesting that we might be adding something every time. So from 2 to 4, we're adding how much? 2, right? From 4 to 7, we're adding 3. From 7 to 11, we're adding 4. Do you see the pattern? What do you imagine we're going to add next? Well, it's probably going to be 5, right? So if we add 5, then the next number is going to be 16. And then we're going to want to add 6. And so the next number is going to be 22. So that's the pattern. How do you describe that pattern? You can say, and you need to describe it so that I could find the next 2 numbers in the sequence if I wanted to. And so you can say that we are adding consecutive whole numbers. Each time. Something like that. Or we're adding 1 more each time, or something. You have to find the words, and sometimes it can be kind of tough. Okay. The next one, the pattern is hard to find, but explaining it is easier once you see it. And one thing you might need to do, and one thing would be helpful here, is if you gave all of these fractions common denominators, right? So you have 1/6. To make this guy make 1/3 have a common denominator, you get 2/6. To make 1/2 have a common denominator, it'd be 3/6. And then to make 2/3 have a common denominator, you'd make it 4/6, right? So now do you see that pattern? What are we adding each time? We're adding a 1/6. So if I add a 1/6 again, we would get 5/6. If I add a 1/6 again, I'd get 6/6, which is actually 1, so we just make it 1. So that's the pattern. That's the next 2 terms. And to explain the pattern, you're simply going to say that we're adding 1/6 each time. And that's it. A little bit easier to describe that pattern. Okay? All right. So that's inductive reasoning based on pattern. There's also inductive reasoning based on data. And so we've grabbed some data here, and we've plotted that data out into a graph. And the graph is all about girls' soccer participation, right? So the year is down on the x-axis. Girls' registration in thousands is along the y-axis. So which of these 4 would it be logical to make a conclusion? Which of these 4 would be the conclusion that would be logical to make? Can't speak. Look at those choices and decide. What do you think? A says more boys play soccer than girls. The graph doesn't say anything about the number of boys that play soccer, so we can't make that conclusion. What about B? More girls are playing soccer today than in 1995. That certainly seems logical, since the number of girls playing keeps going up and up and up. So that's a possibility. What about C? More people are playing soccer today than in the past because the 1994 World Cup games were held in the U.S.
Please come to the main office.
Sorry for that interruption. But the graph doesn't say anything about the World Cup or any reason why the registration is going up. It just says it's going up. So I don't think C is going to make any sense. And then D says the number of girls playing soccer was more in 1995 than in 2001. And that's just plain false. You can see from the graph that that's not true.
Mason Brandenburg, please come to the...
Sorry again. So that leaves us with B, and I think B is the most logical conclusion to make. Now, again, is that necessarily true? No. Something may happen to make the girls' registration fall off from 2001 to 2016, and who knows whatever that is. Playing soccer is bad for your teeth, so people stop playing. I don't know, whatever. That's obviously ridiculous, but we don't know that for sure, so we don't know if that's true, but it's definitely a conclusion that seems logical from the data, okay? And so that's inductive reasoning, trying to make conclusions based off of patterns or data, okay? Now, next section is all about conditional statements. trying to find a logical order so that we can make some logical statements, some logical arguments, right? And so conditional statements are, like I said, logical statements, and they have two parts. They have a hypothesis and a conclusion. And so the idea behind a conditional statement is that if this is true, then I know that this is going to be true. And so we write these conditional statements in if-then form. And they have two parts. They have a hypothesis. The hypothesis is the first part. It's the if part. And then the conclusion is whatever you're going to decide, if the hypothesis happens or if the hypothesis is true. And so that's going to be the then part. That's going to be the second part of your if-then statement, your if-then form. Okay? So an example of a conditional statement might be something like, if it does not rain,
Autumn Zonko